It's a great pleasure to have James Drummond from the University of Southampton, who will talk to us about cluster algebras, tropical geometry, and scattering algebra. Welcome, James.
Okay, thanks, Yorgos, and apologies in advance if this crash happens again. Thank you to Apple for giving me my nice new laptop, which has this new feature. Okay, so I would like to describe some work that we've been doing with my great collaborators, Jack Foster, Omar Gurdogan, and Chris Kalouzios. And there's some related work, which I think we're probably going to hear some more about in some papers of Nima Akani Hamed, Thomas Landmark Spradlin, and also Yorgos Papathanasiou and Nicholas Henke. Okay, so let me just begin with something that I think everybody will be very familiar with. But I just want to remind how we end up relating Grassmannians to the kinematics of planar scattering amplitudes in 4 dimensions. So we begin with some planar arrangement of momenta, pi, scattering amplitude in the picture on the left, and these satisfy 2 conditions. One is momentum conservation, that the sum of the p's is 0, and the other is the on-shell condition that these p vectors are null, so pi squared is 0. And we can solve the first by introducing dual coordinates, and that gives us a piecewise light-like contour in some dual x space, which is obviously related to a Wilson loop, something that many people have worked on and are familiar with. The second sets of conditions, the on-shell conditions, can be solved with spinor helicity variables, and we write p as lambda lambda tilde, and this solves for us pi squared is 0. And the first set is natural when we're considering color-ordered planar amplitudes. So we have an ordering in our external p's. And if we combine both, we can introduce these twistorial variables z by defining mu through the incidence relation, mu is equal to x lambda for each I. And then we identify the pair lambda mu as a 4-component object, which actually is projective because the incidence relation is homogeneous in lambda and mu, and we should mod out by this overall scaling. And then dual conformal symmetry is something which acts linearly on these z's, and the invariant objects are the natural antisymmetric 4 contractions of 4 of these z's. It's just the determinant of the matrix made of 4 of these z's, I, j, k, l. Okay, so we have these n twistors, zi, which define our planar kinematics. And if we think about that, that immediately leads us to the Grassmannian GR for n. We can think of them as 4 n-component vectors of the rows of this matrix, defining a 4-plane in n dimensions. And we should mod out by SL4. That's the dual conformal symmetry. So the total dimension of this, because these are projective objects, is 3n minus 15 for the SL4. And this is the space that I'm just going to refer to as the Grassmannian. And I've gone through this story because there are other talks today in which Grassmannians and tropical Grassmannians will arise in the context of scattering amplitudes. And I just wanted to make a distinction in the way the kinematics arise here compared to the way they arise when we're talking about generalized scattering equations or these stringy canonical forms and so on. Okay, so here the Grassmannian is directly the kinematic space. Now, these Plucker coordinates, or these determinants, zi, zj, zk, zl, they satisfy quadratic relations. That's because if we try to totally antisymmetrize on any 5 of these 4-component objects, we must get a 0. So we get these Plucker relations. And in fact, we can define the Grassmannian through these relations. And so what I'm going to do is I'm just going to switch notation to emphasize that, and I'll call pijkl a new variable, which replaces this determinant of 4 columns made up by 4 of these z's. So with these variables, I write the Plucker relations again. Here they are, these quadratic relations. These generate for us a Plucker ideal in the space of polynomials in these variables p. And now I'm going to do something that's quite brutal, seems quite brutal. I'm going to tropicalize these polynomials. And that means that I'm going to replace multiplication with addition, and addition with taking the minimum. So as an example, I have the polynomial xy plus wz squared plus 2uv. And if I take the tropical version of that polynomial, I'll get a minimum over 3 terms, minimum of x plus y, minimum of w plus 2z, and finally u plus v. And notice that I lost the numerical coefficient in front of the last term when I took this tropical polynomial. Okay, so if I have a tropical polynomial, then obviously each of the arguments of this minimum is a linear function. But because it's a minimum, I'm going to divide my space into regions, distinct regions where I have linear behavior. I'll divide the space into regions of piecewise linearity, depending on which term is the minimum. And those regions are separated by walls or hypersurfaces that I'll call tropical hypersurfaces. And the structure of these hypersurfaces is what we want to study. And this seems like a brutal operation, and in some sense it is really, but nevertheless, what's interesting is that this tropical space actually captures many features of the original space that we started with. In particular, it captures lots of interesting combinatorial boundary structure, which is what we really want to study when we're thinking about singularities of scattering amplitudes. And so that's why tropical geometry is an interesting subject in its own right as a part of algebraic geometry. So let's study the tropical version of this space. So we have the tropical Grassmannian. And what I'm going to do is I'll take the Plücker relations and I'll tropicalize these polynomials. So let's do an example. If we take our example as GR46, which is the first case that's of interest of GR4n for scattering amplitudes, then here I've picked one Plücker relation that I've written down, a 3-term relation, and underneath it I've written the tropical version with this minimum. And so what do I have to do? I have to look for these tropical hypersurfaces, which are the boundaries between distinct regions of piecewise linearity. And since they're between regions of piecewise linearity, that means that 2 of the terms in the minimum have to be equal, because I'm switching from one to the other. And they have to both then be less than or equal to the third. So there are 3 ways of doing that, depending on the 3 ways of picking pairs out of the arguments of this minimum operation. And I've written down the 3 options down on the bottom of this transparency. Okay. Now, we lost the information of the coefficients, remember? In particular, we lost the information about positive and negative signs in our original Plücker relation. But we can recover that information by insisting that we pick only the tropical hypersurface conditions which correspond to picking terms in the original Plücker relation with opposite sign. Okay, and this makes sense if we're talking about variables that have a well-defined sign in themselves. So if we're in the positive region, where all these ordered Plückers are positive, then we can make sense of picking terms with opposite signs. And if we do that, then we see that the first is allowed and the third is allowed, but the second is not. Okay, so we will just take the positive tropical hypersurface conditions. And if we do that over all of the Plücker relations, we'll get a network of tropical hypersurfaces, and that is what we're going to call the tropical Grassmannian. Okay, now there's another way to describe this positive tropical Grassmannian. Described in a paper of Spire and Williams, which we heard a little bit about in the previous talk. And here what I'm just going to do is I'm going to solve the Plücker relations by choosing coordinates. And these will be the cluster X coordinates, but it doesn't particularly matter. It's just that our Plückers now become polynomials in these new coordinates. So for example, I pick this Plücker 1, 2, 4, 6 becomes a polynomial 1 plus x1 plus x1, x2. And now I'm going to tropicalize these. So I replace that polynomial with its tropical version. In other words, I take the minimum over the 3 terms. The first term becomes 0, the second term is just x1, and the third becomes the sum instead of the product. So it's x1 plus x2. Okay, now if I do that over all the set of minors, Plücker variables, then I obtain a fan, and that fan looks something like this in this case. So you see it's a 3-dimensional space. So doing GR46, it's 3 dimensions. I have x1, x2, x3. And then I've got various slices, tropical hypersurfaces in this space. You can see the gray circles sort of aligned with the axes. And then there's a sort of red semicircle, a yellow semicircle, and a blue wedge, all intersecting in a particular way. And the regions between these surfaces are cones. Okay, and they intersect in particular interesting locations. And if I draw the intersection of that with the unit sphere, that's what gives us the solid black lines on this diagram. And the intersection points are black dots. So this fan has what would be a ray emanating from the origin through that black dot. And since it's a dot on the unit sphere, I'll call that a vertex. Those vertices are connected by edges. The edges connect up into triangles. And in this example, I stop because I'm in 3 dimensions. But if I were doing a higher dimensional example, I would go on to tetrahedra and higher dimensional simplices and so on. Okay, now, if I take the dual of the object on the left, I obtain a very familiar looking object, which is the Stashev polytope. So here the black dots have become faces. And I've labeled the faces with the values of the vectors that would be the rays which emanate from the origin and pass through the black dots on the left. So each dot on the left maps to a face on the right, labeled by the relevant vector. Okay, so this picture on the right is very familiar from the study of Grassmannians, moduli spaces, and cluster algebras, in particular cluster algebra for GR46 or GR26. So let me just talk a little bit about cluster algebras and remind you how this picture arises there. So we can associate to a cluster algebra to the space GR4n, or rather its positive part. And a cluster algebra is defined by taking an initial cluster, which is specified by some quiver diagram, looks like this in this case, where each node is labeled by one of our Plucker coordinates, ijkl. Okay, so the basic idea of cluster algebras is that you can select nodes and do an operation called mutation. So if I select node ak, the mutation rule tells me how to get the new value of the node, of that node, ak prime. And it's basically given by the product ak prime is the sum of the product over incoming arrows of those A's plus the product of the outgoing arrows of those A's. And what that generates for us are more A coordinates, and these in general are polynomials in the Plucker variables. And this is connected to amplitudes because we've lots of experimental observational evidence on known scattering amplitudes that are of some polylogarithmic form, that their symbol letters, in other words, their singularities, are given precisely by the A coordinates generated by these cluster algebras. So we have many examples where that's the case. And moreover, we even know that a symbol is essentially an ordered sequence of possible discontinuities that you can take. Consecutive letters in the symbol are also constrained by the cluster algebras. In particular, 2 letters next to each other in the symbol have to appear together in some cluster. So you're not allowed symbol letters that are adjacent to each other that are A coordinates from some random places in the cluster algebra. They must share a cluster. And that's related to the Steinman relations, which we heard about in a couple of earlier talks a couple of days ago. Okay. Now, also associated to each of these clusters and to each A coordinate is a vector, a G vector. And these can be defined by simply taking the unit vectors in the initial cluster and labeling the nodes 1, 2, 3 as I go down the columns and so on. And I associate the unit vector in that direction to that node. And there's a mutation rule. As I mutate the A's, there's a mutation rule for the G's for each node as well. And this gives me a dictionary which maps a G vector to each A coordinate and vice versa. So for each A coordinate, there's a unique G vector and vice versa. Okay, now in our example that we were talking about with that Stashev polytope and the fan that I showed, the GR46, that's actually dual to a GR26, and which is an example of a GR2n. And in those examples, the fan that we defined following the Spire-Williams construction is actually equal to the fan that we obtain by looking at the G vectors for our cluster algebra. So if I just flip back, shouldn't do this, but let me just flip back here. Yeah, I hope you can see that this is, I've gone back to the slide with the polytope, and on the faces of this polytope, you can see the vectors for the rays on the left. Well, these are the g vectors associated to the a coordinates which label the faces of the cluster polytope. Okay, so that fan is the cluster g vector fan. However, when we go beyond GR46, new things can happen. In particular, our next example in the GR4n, but it's also true in other GRKNs, our next example is GR47. And here we have a choice of what we would like to tropicalize. In other words, what we would evaluate as polynomials in the x coordinates and then consider as tropical polynomials. And that's because for GR47, we actually have 42 unfrozen a coordinates. I've given them here. They arise in cyclic classes of 7. And so I've got 6 classes here, and you're supposed to take these examples and cycle them round 7-fold. Okay, so that's 42. And we can, as well as tropicalizing the minors, we can also tropicalize these quadratic a coordinates in the second line. And in fact, for this case, there are 4 natural cyclic invariant fans that you might want to consider. So in this list, in this table here, I've given the 4 fans, and they are specified by the set of minors, or set of a coordinates rather, that we would like to tropicalize. So the second fan on the list, A1 to A4, is all the minors, and that corresponds to the Spire-Williams fan that we were talking about before. The last fan on the list is where we tropicalize all of the cluster A coordinates, and that corresponds to the cluster fan, the G vector fan that you get from the E6 cluster algebra. The first fan on the list is a maximally parity invariant subset, maximal parity invariant subset of all the minors. And the third fan on the list is the parity completion of all the minors, which involves the A5s, but not the A6s, so some of the quadratics. And you see they're all different fans. So they have different F vectors and different substructure. The most refined is the bottom, the cluster, the least refined is the top. And you see, so the first component of this F vector is all of this labels the rays, so that all of them are 42. So they all have the same set of rays. But which rays are connected by edges depends on the choice of fan, and even which edges form triangles depends on the choice of fan. And given a fan, you can generalize the notion of a cluster adjacent polylogarithm that I briefly referred to before by declaring that the allowed pairs should follow the edge structure of the fan, and even the allowed triples should follow the triangle structure of the fan, and so on. So to each fan, you can have something you might call a tropically adjacent polylogarithm, class of polylogarithms. Okay, I can say more about that. But so things already got interesting when we went to GR47. They get really interesting when you go to GR48. Because for n equals 8, we actually have an infinite cluster algebra, and it's of affine type. And this throws up 2 problems immediately. First of all, the most basic, we need a way to select a finite number of a coordinates to be our singularities for a given scattering amplitude, because a given scattering amplitude has a finite set of singularities. Moreover, we also know that some scattering amplitudes have singularities that cannot be a coordinates. They're not rational functions of our z variables, or no rational functions of the Pluquet variables. So the first problem can be solved by picking a tropical fan. So if I pick some set S of objects to tropicalize, minors or a coordinates to tropicalize, I will get some finite object with a finite set of rays. So here are 3 natural fans that you might pick: the maximal parity invariant subset of minors, all the minors, that's the Spire-Williams case in the second line, or the parity completion of all the minors, that's the third line. When you do this, you find a fan, and the number of rays of the fan now depends on which choice you picked. So for the simplest, you have 272 rays plus another 2, so 274. 272 of them are G vectors of the GR48 cluster algebra, and 2 of them are not, they're extra things. And in fact, these extra things solve the second problem above. We find that there are some algebraic singularities that are naturally associated to these extra rays. And I'm going to discuss how, but these square root letters that we know are there show up precisely because of this feature. So let me just briefly describe how that arises. So the reason that you get this infinity in the first place is because you have clusters with doubled arrows in this cluster algebra. And the clusters with doubled arrows all look like this if I delete the frozen nodes, or something related to this by mutating on the A's. So this picks this infinite cluster algebra out as an E711 in the classification of Felix and Shapiro-Tumarkin. So it's an affine cluster algebra. And what we want to do is we want to pick diagrams like this, clusters like this with the doubled arrow, such that all the frozen nodes are pointing out of the W0 vertex, and all the frozen nodes connected to Z0 are inward pointing. And then I'm going to take the B's in the top picture and combine them all via a product and just stick that on the top and call that total B. So that's the product B1, B2, B3. And now I can start mutating on W0, Z0, and I'll get my infinite affine sequence of clusters. So that looks like this. So at the top, I've written this, what we call origin cluster. It has this particular shape at the bottom here. That's reproduced at the top of this diagram. And now I can start mutating on the nodes connected to the doubled arrows. So I can pick, for example, if I mutate on W0, I'll go down to the left to the next picture. If I mutate on Z0, I'll go down to the right, to the picture on the right. And these initial mutation rules are given in the top here, at top left and top right, respectively. And notice now, because we have a doubled arrow, that we get squared appearing, Z0 squared or W0 squared. That's because we have doubled arrows. Okay, so after these initial mutations, we then get a regular sequence, recurrence sequence for the mutation rule, which is again quadratic because we're always mutating on nodes connected to a doubled arrow. And they have this form for the left and the right branch respectively. Okay, so we've got this nice mutation rule. What about the G vectors? So if we think about the G vectors, we find very quickly that as we perform this mutation, the difference between the G vector for the next node, next A coordinate, which I've called Z here or W, and the previous one is constant. It's actually the G vector for W0 minus the G vector for Z0. And that happens in both directions. And since I keep going, mutate, 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 and I keep adding the same difference, and I don't care about the length of these G vectors, I find that the G vectors asymptote to a particular direction, which is given by GW0 minus GZ0. And that happens for both directions, so that they both asymptote to the same limiting vector from either direction. These are the extra rays that we saw in the tropical fans associated to those choices of tropicalizations for GR48. So that's where they show up. The extra rays are not G vectors, but they are limits of infinite sequences of G vectors in this infinite affine chain. Okay, good. Now, let's go back to that recurrence relation. It was quadratic. So I've just written it up again. That was the form of it for the Z branch. And it's quadratic again because we had doubled arrows. But actually that quadratic relation can be rewritten as the determinant of this matrix relation, where if I arrange a matrix of these A coordinates, Zn plus 2, Zn plus 1, Zn plus 1, Zn, then I can get the matrix indexed by n from the previous one by right multiplication of this matrix given by P1 minus F0. So in other words, I can start with the initial matrix, Z2, Z1, Z1, Z0, and put n copies of this matrix, 2 by 2 matrix P1 minus F0, keep multiplying for the right, and I'll get the matrix on the left. And that rule obviously implies a linear recurrence amongst our same set of A coordinates. Zn plus 2 is Zn plus 1 P minus Zn F. And it's equivalent to our original quadratic recurrence as long as P obeys this relation. P satisfies this relation that I've written at the bottom here. Okay, and you can show using that relation and the initial mutation rules that although it looks like I've got a factor Z0, Z1 and P on the right, actually you can easily find a factor Z1 on the thing on the left. And although you can't easily find a factor Z0, you can in its square. And because everything is polynomial, that tells you that I'm allowed to divide by Z0, and this formula for P, FZW0 plus Z1 over Z0, is actually a polynomial, even though it's got a denominator in this formula. So this quantity P is also polynomial, and therefore the linear recurrence relation actually gives you a manifestly polynomial recurrence relation for the A coordinates of this infinite affine sequence. Okay, now I'm conscious I'm nearly at the end of my time, but let me just get to the end here. So if I focus on this linear recurrence, I've written that up now, that would be the Fibonacci relation if we had P equals 1 and F equals minus 1. So that would be dead easy to solve. And with P and F not equal to 1 and minus 1, it's still dead easy to solve because you write down the same generating function, this g of x that I've written here, and it has classic Fibonacci-like denominator, except that now it's 1 minus px plus fx squared. Okay, so we've got this solution to the recurrence relation, and that implies that the asymptotics are dictated by the roots of that quadratic in the denominator. In particular, the asymptotic ratio of the two A coordinates, Zn over Zn minus 1, has to be P plus root delta. That's the root of this quadratic. And delta is given by P squared minus 4F. Moreover, also like Fibonacci, you can just write down an explicit solution for the recurrence relation. I write it down there on the bottom equation. And let me repeat it. So that's written in the bottom, sorry, there. Now let me repeat it up there in the top. And I've highlighted a new feature, something interesting that shows up in this solution. In the red, there's a coefficient to the piece which is dictating the asymptotic. And that coefficient also involves the same root delta. Now, if I take that coefficient and I multiply it by its conjugate with the minus root delta, I get something rational. And that rational object is among the set of A coordinates that were associated to the G vector rays that we got for our tropical fan. So that's nothing new. That's already in the rational set of rays. On the other hand, I can consider the ratio of this coefficient to the conjugate of it with the minus root delta. That's phi z that I've written there.
James, are you there? For me, the speaker got cut. Can others also? Okay, Mark, yes, seems to also.
Yeah, I can't hear him either.
Yes, I think his computer crashed, so we just wait for him to reconnect.
Okay,
let's. I might point out this is called a frozen node.
Yes, indeed, everyone was really, yeah, I would dare say on pins and needles, yes, on what James had to say. It was, I think most of us will agree that it was a very, very fascinating talk so far. It really just happened. I don't know. It really feels as if it happened on purpose, like, I don't know, 24 hours episode or some series where all the action is deferred to the next episode. But let's
We're
hope
making
that
too much progress. God wants to slow us down.
Or like the old Batman series, yes, same bat hour at the same bat channel. James, are you back?
Yeah, I'm sorry about that. Of course, the inevitable happened. So, what do you want to do?
It's all right. We were saying that it happened almost as if on purpose, right at the climax, right at
Yeah,
the
right.
Yes.
And by magic, oh, sorry, I have to go.
All right, guys, we'll have to stay on time to make it for Freddy's talk. So are you able to see your slides?
Yeah, I can see my slides. Can you see them?
Yes, can you make sure that they can be they can move forwards and backwards?
Yeah, so you need to put me back as you need to put me back as
Nastya is yes, okay.
Yeah, I'm the only one who can do it, and I just did it.
Okay, thank you. I'm really sorry about this, guys.
Could you please check your slides?
Was I on this transparency?
We
Sorry,
can't see your slides.
Sorry, let me just, I'm sorry, I need to screen share again, sorry. Can you see?
Yes, so you need to make it a full screen.
Yeah.
On that, I think it's good. All right, yes, please
Is
go
this
ahead.
where I was?
Yes.
Okay, I'm really sorry about this. So, we took an explicit solution for our recurrence. And now I'm going to read off these coefficients and I get these ratios, phi z, phi w. And the ratios are new. The products are not new. They're comprised in the rational set that we already got from the G-vector rays. The ratios are new. And this P and F that I introduced and the delta, therefore, they only depend on the limit ray that I get from doing this sequence. The ratios depend on which path I took towards that limit ray. And depending on the fan, well, on our smallest fan that we took, each limit ray has 32 origin clusters, and then each one has a Z branch and a W branch, both which asymptote towards that ray. So this square root delta, in that case, is the 4-mass box square root. So that's something we know we need for scattering amplitudes. And moreover, this phi z, phi w, there are many of them, 128 in total for that fan, because I've got 32 times 2 times 2, because I've got 2 rays. I have 128 of such ratios. They're not all multiplicatively independent. And in fact, there are 18 of them, which match exactly the 18 letters that were found in a recent 2-loop NMHV octagon computation. That's by these authors at the bottom. Okay, so that's where I wanted to get to. The combination of the tropical geometry, choice of fan, and the cluster algebra together allowed us to extract a finite set of singularities and new square root singularities, which are precisely the ones that we want for our scattering amplitudes in the octagon case. And okay, I leave my summary slide here, and I apologize again for my wonderful computer crashing, and let me finish. Thanks, guys.
Thanks, James, for this beautifully clear and fascinating talk. Let's all thank James. And I see there are many questions. Michael Shapiro already mentioned something in the chat, so I will respect this order and have him talk first, maybe come back to this comment or add something else. So please, if you hear us, you're welcome to unmute yourself and ask.
Hi, everybody. Thanks for. Yeah, so it was just a reference comment that this notation E711, it's not up to us, it's due to cite, some paper about elliptic singularities, but it was not my question. So my question was about these extra rays for that you described. So you choose two special affine sequences and you get as limit the G corresponding G vectors. Is it any reason why you choose these sequences? Because I can imagine that you can choose, what is so special about exactly these sequences of mutations?
So these are the ones which asymptote to these rays. So we know which rays we're looking for.
Oh, okay. So, but it's kind of reverse engineering, right?
Yeah, yeah. So,
so
we construct the tropical fan and we find 274 rays, but we can only immediately identify 272 of them as G vectors.
Okay.
So we know that there are two extra interesting new things. Mm-hmm. And then those new things arise as limits of G vectors under these affine sequences.
Okay, so it's basically you knew the answer from the very beginning, and then you construct the sequence which gives you this.
We knew which rays we were looking for from the tropical fan, and then we found the sequences of clusters that asymptoted to those rays.
But may I also say we consider all possible subaffine A2s and look at them, and they all asymptote to the rays we want to.
Yes, I mean, maybe it's worth saying the other fans in this list have more extra rays, and so there are other affine sequences that asymptote to those. And presumably you can pick even more refined fans by picking bigger sets of A coordinates, and they might yet have extra rays. We haven't investigated that, but there are certainly other infinite limits. You're right that those are not the only affine sequences.
Yeah, but what I meant that I can imagine that there is an uncountable number of different rays that you can obtain by choosing different sequences, right? So is there any kind of axiomatic way to see those who are interested for you?
Yes, that's right. So we know which ones are interesting by our choice of tropical fan. And there are certainly infinitely many. I don't know if they're uncountable, but yes.
I'm sorry, can I interject a relevant comment? We believe that every other exceptional ray, there are infinitely many, and all of them can be generated from these two by an element of the cluster modular group. So in some sense,
that might be, yeah.
Yeah, that's what we believe.
Well, just last question. So do we have like some notion of equivalence pair, so that you have pair of, I believe this is not two rays which have this property. Maybe you can, if you can choose other pair of extra rays, they also have this property that all others can be obtained from other one by infinite limits. So there is some equivalence relation here. Is it true or not? Yeah.
Are you asking me or to Mark?
Boss, I don't know.
I'm confused by your question, but we should take that offline. I believe the answer is no, unless I misunderstand. There is something very special about these two. But
oh, yes, actually, yes. Maybe I can add a comment on that. The order of the polynomial key goes up.
Thanks, James. That's right.
So, so this is sort of the two for that smallest fan. They have the P of the lowest order, which is
I see.
quartic, I think, or is it? No, yeah. Anyway, it's quadratic, of course. Sorry. Yeah.
Thank you very much.
Okay, it's great to have also some mathematicians, yes, attending and asking very interesting questions. Let's move on to Lance Dixon, who raised his hand. Please go ahead, Lance.
Thanks. Hi, James. Nice talk.
Hi, Lance.
So can you go back to that slide you were at before with the, say, the n equals 8
yes.
Original? I mean, it's just a question of, so you found sort of a subspace or a way of looking at something that's smaller than the infinite cluster algebra. How does that correspond to you know, the likely function space that a given loop order amplitude will fall in as a function of the loop order?
That's an excellent question.
Actually, I'm even more interested currently in the 7-point case.
Right. And let me go back to, that's also a good question.
Go beyond symbol levels. So
yeah. So already at 7 points, it's not totally clear which fan should be applicable to which amplitude. So far, the evidence that we have is that the smallest fan in this list is applicable to MHV 7 particle amplitudes. But the third one in the list is applicable to NMHV 7 particle amplitudes. That's consistent with what we know.
Sorry to interrupt. In principle, that statement is at symbol level for you, and we can check whether it also agrees when we add zeta values, correct?
Yeah, everything I'm saying was observed on the level of symbols. That's right.
Okay. Sorry. Go ahead, please.
So anyway, the general point is that we don't yet know the full pattern of which fan you should pick for which amplitude. The smallest one that you can reasonably pick does seem to be applicable for, let's say, the simplest amplitudes, so far that we know. But we don't know the general pattern.
Thank you.
Let's move on to Claude Dur, who also raised his hand. Go ahead, Claude.
Hi, James. Very nice.
Hi, Claude.
I have a question which is similar to Lance's and maybe with the continuation of it about what you can possibly infer about a function space. So now that you have at least a hint of what the geometric origin of this algebraic letter is, so the square root of the Riemann box, does it give you a hint or a suggestion whether this root can be rationalized or whether it's impossible to rationalize it via some other choice of coordinates or some other change of variables?
I don't know the answer. So yes, it doesn't give me a clue as to whether or not you can find clever coordinates that rationalize. Just that in these coordinates, it's definitely not rational. Yeah, maybe somebody else knows better or based on the theory of these affine sequences, but I don't know the answer. It's possible that maybe you can find clever changes of variables that would rationalize phi z, phi w for you. It's not obvious you can do that and preserve the rationality of everything else that you had.
Yeah, of course, that's what I meant. Something where the whole alphabet would be rational in the end.
Yeah,
Okay.
yeah, I don't know.
Okay, thank you.
I know there are 3 more people that have raised hand. For the sake of time, since we are 25 minutes past, would you agree to wait for, let's say, the break and then more informally ask the speakers? James, you will be around, I guess, during the break, right?
Yes, I can try to be, and again, apologies for that crash.
No, it's fine. I guess, Nima, you're okay with waiting, so if Nima is fine, then I guess all of the questions can wait. And thank you very much for the, again, very, very nice talk.
Thank you.